In this video, I'm going to talk about a couple of race condition patterns that are very common when you're working with concurrent programming. And these are things that you really need to be aware of, right? So these are two patterns that you will see over and over again when you're working with concurrent programming in Java. Let me start with an example to illustrate the first pattern, right? So here is the piece of code. I have an if condition here, which is checking if a certain value is equal to 0, then I'm printing something to the console. All right. Now, if I were to ask you, what is a value that gets printed to the console? What would your answer be? Well, simple to find out. This is 0, and I'm printing value plus 1, so it'll be 0 plus 1. What gets printed to the console should be 1. Simple? Seems simple. For concurrent programming, not so simple, right? So if it's sequential programming, there's just one thread running, well, this is fine. But with multiple threads, you kind of might have figured this out already. Okay, so here is an example of multiple threads, kind of wreaking havoc on this thing. So let's say you have this thread, which is what is executing our if condition that we just saw. Okay, if value equals 0, print value plus 1. Okay, now if value equals 0 is executed by one core, the core that's running this thread, copying over the value of the value variable from memory into a processor cache. Okay, a level 1 or a level 2 or even a level 3 cache. Now this happens and it has copied over the value of 0, and now it has to execute the next statement. But before it executes the next statement, let's say thread 2 had a value equals 10 execution somewhere. Maybe it did the value equals 10 before this thing, but this updated value was sitting in the cache, or maybe it did it between these two instructions executing. Okay, it updated the value, and this value gets written to let's say a level 3 cache. Now when this value 10 is written to main memory, if this thread is not reading from the main memory again, well, it is going to print maybe from the cache, and it's going to print value is still 1, even though the value has been updated over here. But let's say the operating system scheduler takes this thread out, brings another thread into this core, and then once that thing is done, then it brings this thread back, and now it's going to say, hey, now I need to print value of value plus 1, and it's going to say, okay, let me read from memory. Value happens to be 10 at the time, so when I'm printing, what you get is 11. Okay, so the value of this value variable when this if condition executed is different from the value when the print statement executed, and this happened because there was another thread that updated the value of this variable between these two statements. All right, this is very much possible because both these threads are running in completely different cadences, right? They are completely different things, but they happen to use the same value. They're accessing the same value, they're reading and writing to the same value, and this is the problem. This is a pattern that we see a lot. This is a pattern called check then act, and this is very, very painful to do in concurrent programming. So you want to check for something. If this, then do something else. You're acting on that variable. Okay, you're either updating that variable or you're doing something else which has a side effect. This is tricky with concurrent programming because, again, like I said, there is a gap between check and act. Okay, so check, the value might be something for whatever you're checking, but by the time you're acting, that check may not even be applicable because the value has changed in the meantime. Check then act is a common pattern, and you cannot be guaranteed about what the work is, what the output is, based on what you're looking at in the code. It could be anything in the case of multi-threaded programming. The second example, which illustrates the second pattern, is this particular thing. Well, this is, can't get simpler than that, right? It's just value plus plus. Have a value in the value variable. Let's say it's 10. I do value plus plus. What is the behavior? Now, right now you might be thinking, well, are you crazy, Kaushik? I have been working with Java for so long. You can't ask me such stupid questions. This is obviously going to be the value plus 1 assigned to value. Well, yes, for sequential programming, that is true. But for concurrent programming, all those assumptions go out the window. The thing about something like this, the value plus plus or related things, when you'll understand what this is when I explain the pattern here, is that this is not a single statement. Value plus plus is a single line in Java syntax, but when a processor executes it, it's not one line in assembly code. It's not an atomic operation in assembly code. What the processor needs to do when you do value plus plus is something like this. First, it has to fetch the value from the memory to the processor cache. Okay, then it has to increment the value. The core working on this thing is going to increment the value, and then finally the incremented value has to be written back to memory. So now you should see where this is going. Okay, let me give you the thread diagram again. So these are two threads This guy is doing the value plus plus that we have seen, and this one is doing the update, another update to value. Okay, so you have a read the value from to the cache, and then before you write the value back to memory, you're doing a update of the value. So when you write the value back to memory, this value has actually gone from, let's say this was 0. Okay, this has gone from 0 to 10 to 1. Okay, so it's not very straightforward. It's like, yeah, it increments a value, but it's not that straightforward. It increments what value it had before this thing executed. This is a mess. So this pattern is called read, modify, write. This is also a very common pattern. Just like you have a check, then act pattern, you have a read, modify, write pattern, which is also something we do all the time when you're working with values in any programming language. You read it, you update it, and then you write it back to memory. Right? Seems like second nature when you're working with a high-level programming language, but if you understand that these steps, what seems like individual steps, actually maps to multiple steps in the processor's execution, you'll begin to realize that when you have multiple threads, these things can get interleaved, and it's very hard to predict what the value will be at the end of this execution, because there could be a bunch of things that happen in the meantime. So these are what are referred to as race conditions. Okay, race conditions, it's not that these values are racing against each other. It's kind of, think of it as these multiple processors are working on something, and what ends up being the result really depends on when a certain thread performs a certain action. Right? It's all dependent on timing. It's not dependent on whether a piece of instruction executes or not. Because if it's just a single thread, it's very deterministic. If this line executes, you can say, hey, this is exactly what happens at the end of the execution of this line. But when you have multiple threads, it's not just enough to see what code was executed. It's also important to understand what's the order in which it was executed, right? What was the initial state? What was the state when this particular thread got scheduled? It's confusing and it's messy. So this is a problem because of the way in which these processors work. Now the question is, how do you solve this? Well, I'm glad you asked. We'll figure that out in the next tutorial.